Good evening. Welcome to the Bendigo Amateur Radio and Electronics Club. With me is Mike VK3AHA, a veteran of the Apollo program, amongst many other things, and his talk this evening is on the efficient use of the HF spectrum. So without further delay, over to you, Mike.
Thank you kindly. Okay, I thought for starters, I'm going to have a look at a very sophisticated piece of equipment at the end of the night, but I thought we'd take a little bit of a trip down memory lane and have a look at some of the history of communications and just how hard it was for some of the early guys that wanted to get at it. So we're going to have a look at the history of communications and the required occupied bandwidth. You might be a bit surprised when we get down to there. Also, something else that's very important that's cropping up around the world is attempts to acquire part of the non-amateur amateur spectrum. Oh, I've got one. Okay. For non-amateur communication, there's quite a bit going on at the moment with people in several countries around the world trying to grab some of our megabytes of allocation, and it's not going to happen. And then we're going to have a look at a piece of equipment that hello. One. Okay, that's better. All right, so I'll start at the top there again. We're going to have a look at the history of communications and the required or occupied bandwidth. We're going to have a look at attempts by various other commercial organisations to get their hands on some of the amateur allocations. We'll have a look at a very sophisticated piece of equipment that allows us to put a number of channels on a single HF carrier. And then we're going to have a quick look at the end of how we understand those crazy numbers that ACMA come up to put on our licences to actually designate our emissions. Just as you can tell, if your neighbour is using a welder in his garage by the interference on your radio, interestingly, it doesn't matter if you're listening to AM or FM, the noise is present on both bands. In fact, the RF energy generated by welding arc extends from the lowest receivable frequency up to and above visible light part of the spectrum. Early experiments with radio transmissions employed a signal generated by spark transmitters. During the latter part of the 19th and earliest 20th centuries, several young men with inquisitive minds spent considerable amounts of money to get on the possibility of communication beyond the visual range. Previous to their time, messages have been sent by flags or signals lamps. Two brilliant theorists were Michael Faraday for his work in capacitance and James Maxwell for his theory of electromagnetic waves. Proposed the theory of modern electronic communications. They were the theorists. They were the guys that knew that it was possible to do it because the mathematics in their brain told them it could happen, but they didn't have the wherewithal to do the physical work of producing the generators and the receivers. So if it weren't for them, we wouldn't have been doing what we're doing at the moment. Two other guys that took it further, the next stage, were Hertz and Marconi. Hertz was a brilliant German physicist and experimental who's demonstrated that electromagnetic waves predicted by James Clerk Maxwell actually exist. And the other one, of course, everybody accredits the radio to, is Marconi. Developed and demonstrated and marketed the first successful long-distance wireless telegraph in 1901, broadcast the first transatlantic radio signals.
Can you turn the music off?
Can I turn the music off? I can turn the music off. That's your 10 years ago. Okay, Marconi and Hertz concentrated on producing carrier waves for their progression from cable-based telegraph systems to cableless or wireless systems. Two other equally gifted gentlemen, a guy by the name of Sideband and Alexander Graham Bell, applied their expertise to the transmission of voice over Hertz and Marconi's radio waves. On December the 24th, 1906, at 9:06 p.m, Reginald transmitted the first human voice over the radio from Brook in Massachusetts to ships in the Atlantic, owned by the United Fruit Company. Reginald began his broadcast with a recording of Handel's Largo, and then he played some little note on his violin, O Holy Night. Have a look at what the date was and you might see the connection there. Alexander Graham Bell is often credited with being the inventor of the telephone, since he was the first one to be given a patent for it. However, there were many other people, inventors such as Elisha Gray and Antonio Mercy, who developed the talking telegraph. Credit must be given to Emil Berliner, who invented carbon and diaphragm microphones. So a lot of work went on there for people other than we normally give credit to. Together, these gentlemen developed a system that could provide communications from one side of the continent to the other, from one nation to another, and even to ships at sea. However, the challenge required serious engineering to resolve. A single transmission occupied a large amount of the bandwidth and could be heard globally. Spectrum output from a duplicate of the Titanic's 5 kilowatt transmitter. They actually did build it. I had a look at a picture of the Titanic sitting on the floor of the ocean. The radio room was right at the top of the first class deck, so the feed to the antenna was as short as possible. And it's still intact there. It didn't get crushed or damaged because that's the way the Titanic settled on the ocean floor. And it was quite a startling picture to see that this room, which was probably one of the last ones that had anybody in it, is still intact on the deck of the ship. Spectrum output of the duplicate 5 kilowatt spark transmitter operating in the 300 metre band, that's at 1 megahertz, and the 600 metre band, 500 kilohertz. The vertical scale here is 10 dB per division, and the horizontal is 100 kilohertz per division. It is reasonable to expect that minus 6 dB bandwidth of the Marconi peak transmitter in the order of 50 kilohertz to 500 kilohertz, so 10 to 1 range, but 6 dB. Okay, they're talking about it being a 5 kilowatt transmitter, 3 dB makes it 2.5, another 3 dB makes it still over a kilowatt that's pumping out all across the whole of the band. No wonder they could be heard worldwide. The other problem with them was that the antennas were extremely large. Each tower is just under 150 foot high, and the spacing between the towers was around about 200 feet. Marconi wireless station antenna at Cornwall. The steel towers replaced the wooden ones destroyed by a storm in 1901. And that's the station after the storm went through. It just annihilated it. The third thing they had to come up with was large amounts of power. Look at the size of the conductors there. Enormous amounts of current flowing in these magnetic loops to provide the energy that they needed for very, very high-powered spark generators. Let's go back way back in time. The Romans originally used bonfires to communicate messages over long distances. Basically, a series of bonfires were erected on hilltops from the scene of the battle to the capital city or the town, in much the same way as we use repeaters today. How long would it take for a message to get from Istanbul to Rome today? Since the route would be taken over land, consisting of about 3,000 kilometres and about 1,400 kilometres from Rome to Istanbul, including a sea crossing for almost 1,800 kilometres from Istanbul to Alexandria. And since it took over 63 days, 2.5 months, or a little over 5 months, to get a message. We want sound there now. I can get it here.
Like, treat a second landing? Everyone will want to know. Did curiosity survive? There's a possibility we won't know, at least not right away. During its descent through the atmosphere, Curiosity must switch to a new antenna for each transformation it makes. At each switch, we could lose lock on the signal for a short time. That won't hurt the rover, it just means we won't know what's happening right away. Even with a solid signal, the communications link direct to Earth only works during the first half of the rover's descent. Why? Like Earth, Mars is spinning, and during landing, Curiosity and its landing site will disappear from view like the sun setting. Out of sight equals the end of direct radio contact. But NASA has 2 spacecraft orbiting Mars that can help. For the second half of Curiosity's descent, the Mars Odyssey orbiter is in a good place to pick up the rover's signal and send it right back to Earth. To best hear Curiosity's signal, Odyssey must rotate about an hour before landing. That sounds easy, but engineers are asking Odyssey to perform a maneuver it's never tried before. Will it work? Probably, but it's not a sure thing. If Odyssey doesn't rotate successfully, never fear, the rover won't be affected whatsoever. Once again, it just means we have to wait longer to hear from the rover. Odyssey could perform as hoped, but we're still not home free. Engineers always think of what-ifs. For instance, what if the rover lands on a slope? If so, the low-flying Odyssey orbiter might not be able to pick up its signal. Even if everything goes according to plan with Odyssey, there's a final challenge: time. The rover may be standing safe on Mars, but Odyssey has to be quick in getting the signal. Odyssey is moving fast. It will only be in the line of sight to hear from the rover for a few minutes, perhaps no more than 5. So the Mars Reconnaissance Orbiter plays the role of backup. It will also fly overhead to capture what happens and then store the landing data it collects on board for playback to Earth a few hours later. Engineers then have to decode the data, which takes several hours. Sometime in the middle of the night for Curiosity's mission team, it's possible that the orbiter could tell us the rover's fate. Or there are other scenarios where the rover might be perfectly safe, but we might not hear from it for 3 days. That's all to say, Curiosity's landing is filled with drama, and we'll need lots of patience. No wonder they call this rocket science.
Does it astound you to understand that we have not 1 but 2 spacecraft in orbit of our planet that we've never been to, that we know very little about, and yet we managed to put 2 spacecraft in orbit around it and they can act as relays to relay the information from the rover on the ground? I find that absolutely astounding. NASA complains about the 20 minutes plus delay in the messages from Mars. They'd like to see them a little bit quicker. I suppose they would. Around the turn of the century, Alexander Bell listed the Bell Telephone Company as telegraph and telephone systems, and Marconi listed Marconi's Wireless Telegraph Company in 1900. One of the major customers for the increasing communication network was none other than the railroad. Put that in there because it indicated that the 2 of them, Marconi and Bell, were serious about what they wanted to do, so serious that they were prepared to put their own money into listing the companies on the exchange. Railroads needed communications, much as they do today. Bookings, ordering of fuel, supplies, and advice of delays. So the railroad network expanded worldwide. Along each track was a wired network of telegraph systems. The Great Western Telegraph in the UK, you can see the pole in the background there with many, many circuits on it. The transcontinental being built across the US of A, and guess what? The telegraph poles are there before they've even finished putting the track down. So that shows how important it was. Here in Australia, the railways of South Australia, and that's the Melbourne to Adelaide Intercapital Express. It was a rugged old sort of trip, but the photo is there because it's got on the left-hand side several bearers down the pole and a few local bearers on the right-hand side. The first US patent applied for single sideband modulation was filed in December the 1st, 1915 by the US Navy, experimenting with single sideband over radio circuits before World War I. Single sideband first entered commercial service on January the 7th, 1927, along with a long-wave transatlantic public radio circuit between New York and London. Amateur radio operators began serious experimenting with single sideband after World War II. Strategic Air Command established single sideband as the radio standard for its aircraft in 1957 and became the de facto standard for long-range voice audio transmissions since then. Single sideband transmissions referred to FM as the mode most suitable for emergency communications may be required. A characteristic of FM is a condition known as capture effect, whereby weak signals are completely blocked out by stronger ones. It is often the weaker ones in emergency that need to be heard. So the weaker stations, weaker traffic on the AM channel is, the AM channel is used exclusively for aviation services in the 118 or 136 meg band. That's just a straight out AM service. The reason for tonight's presentation will be limited to AM and single sideband. The existence of a network of copper telegraph and single-core wire-lined telephone circuits enabled the progression to frequency division multiplexing simply by upgrading the terminal equipment. The most expensive part of all of the telegraph networks was in fact the wire. Amateur radio came into being after radio waves were adapted from commercial system in the 1890s by the Italian Marconi. Amateur wired telegraphists set up their own interconnect telegraphic system. So before we had radio, they actually had wired connections, copper wires down the street, under the street, wherever they could, and they had their, much the same as we have nets with our radio, they had their get-togethers on their wired circuits. Magazines show continual progress by amateurs, including a 1904 story in two eighth graders constructed a transmitter and receiver with a range of 8 miles, and in 1906 a story about 2 Rhode Island teenagers building a wireless station in a chicken coop. In 1910, the Amateurs of Australia formed the now Wireless Institute of Australia, and that's the longest standing single operating body for amateur operators worldwide. It still remains that way today. How wireless interference helps sink the Titanic? It would be more something like to mention the Titanic when we talk about early HF radio. We tend to think of wireless service interference as a modern problem, but in 1912 the airways were a wild frontier. Competing signals weren't just an occasional occurrence, they were an expected and accepted part of radio communications. Remember we said that there was 2 frequencies, the meg and 500 kilohertz. The whole of the shipping of the world that was trying to communicate via radio was trying to use that. Could you imagine if they took away all of our HF channels and gave us, say, one on 40 metres and one on 80 metres, one channel each? Can you imagine the pile-ups that we'd get? It would be incredible. Radios in 1912 were crude mechanical devices. They sent Morse code by belching ticks of electromagnetic radiation in all directions by passing arcs of high voltage AC across an electric gap, hence the spark transmitter. The Titanic carried a 5 kilowatt synchronous rotary spark discharge transmitter, which used a spinning blade lined with electrodes to emit the 500 kilohertz tone. So they were MCW, modulated CW. The Titanic's machine and most other only broadcast on 2 channels, and this effectively promises that only one single channel could be on the air for hundreds of miles around. Radio operators had unofficial rules about taking turns on this extremely limited spectrum, like waiting turns and bowing in and out of important transmissions, but mostly a fellow operator and a nearby ship. But mostly with good manners, and not only honoured by the Titanic when it was she needed them most. Fellow operator on a nearby ship, the Masaba, sent the following message the day before the crash. In latitude 42 north to 41.25 north and longitude 49 to longitude 30 west, saw much heavy pack ice and a great number of icebergs. So it wasn't as if they weren't aware of the fact of the dangerous waters they were sailing through. So, at the time, the Titanic was transmitting a backlog of private messages from the ship's wealthy passengers to the shore station in Newfoundland. When the warning came through and interrupted his desk, officer Jack Phillips snapped back at the ambassador, "Keep out, I'm working Cape Race." So, yeah, it wasn't as if they didn't know what was ahead of them. They just were, I guess, pressured by the people that were paying megabucks to be on the ship to get messages to Newfoundland. In fact, Phillips, the radio operator, got really annoyed and yelled out at the other one who'd interrupted him, "You fools, stand by and keep out." We can't draw parallels between the rudimentary spectral landscape of 1900 and the device-driven landscape we have today. But so many spectrum management could have prevented the sinking, like if each transmitter base station was tuned to a unique frequency. Unfortunately, technology had not developed to that level. Ensuring priority messages were always respected, whether the airwaves were full or not. In fact, the tragedy contributed to the fast passage of the Radio Act of 1912. So, even though there were so many people lost when the Titanic went down, it did make the governments get together and do some of those things I spoke about there. It's simple operating procedures, but make things much, much easier in the case of an emergency. Attempting to correct the rudimentary spectrum management problems that contributed to the Titanic's failure, to acknowledge the warning, whatever the root cause is debated, and the confused response that followed. It was the first instance of radio regulation in the US, an important step towards the modern rules like the FCC. Now, this is something that I mentioned earlier, and I wanted to spend some time looking at it. Attempts by commercial operators to have amateur allocations change from primary to secondary, or to have secondary allocations assigned to non-amateur use. For some time now, the term use them or lose them has been used in respect of the spectrum space, in particular with respect to the 144 MHz and 73 centimetre amateur bands. However, there has also been applied to the HF 1.5 to 30 MHz frequencies. A new French CEPT paper still wants to get hold of the 144 to 146 MHz from the aeronautical band. I don't know if you've been following it at all, but they put a application up to the ITU to grab what's the bottom 2 megs of our 2 metre band, but in France that's all the 2 metre band is, it's only the 2 megs wide. They went to grab the whole lot and tack it on top of the 118 to 136 existing aeronautical band. It was rejected by the ITU and we thought that might be the end of it, but the French administration has renewed its attack on the amateur radio 144 to 146 band ahead of the key meeting in Ankara on the 26th to the 30th of this month. Keep your eye on that, and yeah, let's hope that it gets thrown out of there too. Just a little bit about what they're proposing. In the paper to be considered at the conference, the French administration says it's not at this time seeking primary status for the aeronautical mobile service in 144 to 146. However, intent is still there that the aeronautical should share the amateur 2 metre band. It is clear that when such sharing would inevitably lead to amateur operation in the band, would only be tolerated if there was no interference with the aeronautical mobile service. Radio emission might be subject to heavy restriction and low ERIP. Now, what they want these frequencies for is the spectrum by Thales, it's a pretty big organisation, for a range of GPS spacecraft in the Galileo constellation. That's not the constellation, it's just the name of the company. These satellites broadcast a continuous carrier with GPS modulation on top of it, and there's no signal reception interval per sec. So you can try and get some 2 metre activity in, you're going to have to fit it in between the spacecraft going overhead, or hope that they go down for some reason because they're transmitting continuously. It was initially said the Galileo constellation would amicably share the allocation of the amateur operation and could continue, but now France says that unregulated use of the band 1200 to 1300 by amateur service is serious source of harmful interference to the radio navigation satellite service receivers. So they've already done it once on higher frequency, and they've ended up pushing RC up. Another one that's under attack is the 220 megahertz band, which is allocated for amateur service in the US of A. It's under attack by mobile phone companies for a cellular service in the metro and sub-metro regions, and this would not be a shared service but a complete sellout for the amateur service to the phone provider. They've got the same situation in America as what we've got here in Australia, where the telephone companies just want to grab every last little kilohertz of spectrum space so they can get their hands on to earn some dollars with it. How can you show the use of the amateur radio allocations? Well, firstly, announce your presence on air whenever you're mobile. First thing you should do when you get out and get everything sorted where you're going, grab the microphone, give your call sign and say you're listening on the repeater or you're listening simplex on a particular frequency. Let people know you're there. Acknowledge the calls of other operators when you hear their mobile calls. If you're at home getting them some breakfast or something like that and you hear somebody there, whether you know them or not, it's good to meet someone you don't know or say hi to someone you do know, but come back to them and acknowledge their presence there. It's just a matter of showing the governments of the world that we are actually using the airways. We're not just having them there and leaving them silent. And make your club available for marshalling duties. In fact, involvement with any community activity where communication will be considered. It does an enormous good to raise the presence of the club within the community by just making sure that whenever there is a possibility for us to assist, we do it. And for number 4, wherever possible, present a public outfile of your club's activities within the community. This one might interest you too. Norway turned off its FM radio network, replacing the digital radio. Now, a survey found out that something less than 2 million cars in Norway have digital receivers. So the rest of them just don't have any entertainment now. It's gone. This is not an amateur band, but it's being relocated, demonstrates the regulators believe that we are in an internet-driven world. This is a nice bit of equipment I talk about. It's a way of getting several channels onto one carrier. So let's have a look at a typical lower sideband transmitter and receiver. And if we change the filters around, it becomes an upper sideband receiver. That's not very hard to do. If we in fact put the filters in an arrangement where we have one for the left and one for the right hand, for the upper sideband, and do the same for the lower sideband, we end up with a device that looks like this. We have an AF amplifier, a modulator, and we produce one sideband with that. The other one comes through, we don't modulate, it's just straight out sideband from 300 hertz to 3 kilohertz. We add that to the other one, and then on the other sideband we do exactly the same thing again. So here already we've got 4 channels on one carrier, and believe me, that works. It's been used for a long, long time by the overseas operators, and they can get 4 channels off of one carrier. But wait, we have more. You want some more? Okay. How about we chuck another 6 channels in for telegraph? So we've got an AF amplifier, a balanced modulator. We come out with 3 kilohertz to 6 kilohertz out that low pass filter, goes in the adder. We have 0 to 3 comes through without any modulation on it and goes into the adder. And then the other sideband, we have the same duplicate as what we've got on the top. So it produces 3 to 6 kilohertz. And then in the section that we actually we invert, we've got a device which puts 6 telegraph channels on there. with specific frequencies, 700, 900, 1100, 1300, 1500 and 1700 hertz. They're all sitting there as frequency shift keying tones. So the end result is you end up with 6 and 3, 9 channels altogether on one carrier. How would you like that? You reckon that'd be a useful use of the spectrum? Rather than what we do at the moment, where we have a lower sideband, we ignore the upper sideband, we ignore anything else that we can do with it. Why might we do this? We have 3 sideband voice channels and 6 telegraph channels on one carrier. You may ask why, in the environment of satellites, there is no location that cannot be serviced. However, let's look at the cost of the service. You look at a very small island in the Pacific and have a look at their annual revenue that they've got to run the island, and someone comes up and says, well, put a satellite service in for you, and then you can get really crystal clear communication. The trouble is, outright purchase price for a single channel satellite system is $2.5 million for the ground unit. That's all right if you can raise that sort of money, but then there's an annual service delivery charge from the people who own the satellite, and it's around about $94,000 to $95,000 a year. The other alternative would be a 9-channel HF radio TX pair, about $20,000 on radio transmitter and receiver pair there. The installation, around about $1,000, and the antenna, dipole or rhombic, about another $10,000. Annual license fee is $100. Much, much more attainable for a small Pacific island than a full-blown satellite system. And that's the end of it. Thanks very much. Any questions?
A lot of that takes my head, but why did Radio Australia stop transmitting to the Pacific Islands? Why did I'm assuming with Radio Australia no longer transmits to the Pacific Islands?
Basically, their antenna systems that they had set up in Shepparton and Darwin had been built to favour transmissions to the Southeast Asian countries. And the Pacific Island countries were in fact off the back of the antenna. So you had their option was to either transmit at night time and go a long round to get to Pacific Island, or try during the daytime and have very, very poor quality. Much, much easier off the front of the antenna to fire into Southeast Asia.
Well, recently though, it was a government decision to stop broadcasting, unfortunately, but yeah.
I think there might have been more argument had it been a good service in the South Pacific Island, but it was a lousy service, so it was easy for the government to say, we'll shut this down.
I remember a couple of times I went on a cruise in the South Pacific on a ship, picked up Radio Australia crystal clear on a little cheap radio, and it was fantastic to listen to ABC from home. Out in the Pacific, can't do that anymore. And as Mike said, you can have really expensive satellite systems in these places, or use really good, efficient shortwave HF services that can get in everywhere very cheaply. But that's a whole different story.
$2.5 million, is it more than the total revenue in running some of these islands for a year? When they write their budget, it's less than $2.5 million to run the island. And someone comes along and says, I'll put a satellite system in for you. It's only going to cost you all of your next year's budget to do it.
As we found out from aviation a couple of months ago, the infrastructure is not all over the archipelago of the islands. If you've got a half a dozen islands clustered together, the satellite down station or up station, whatever, is on one of them, but the information may not find its way out to the other islands without additional infrastructure. So it's a fairly lousy way to go about it. HF would be far more effective in a situation like that, even if you were retransmitting the information, I guess. Yeah.
With the use of the right frequencies, you can get very good quality HF radio service. You can, especially as point to point, you get to know what frequencies to use every day and when to change them in the seasons of the year. Very good quality.
I've spent a bit of time around various parts of the Pacific, and one of the issues is that the people that we're talking about that were using this service don't have a lot of disposable income, and I mean they really don't have a lot of disposable income. They can buy a Chinese shortwave radio like a little Texan 902 or something for about $30, and that will sit in the village, and they can have that in their house. They can't afford a satellite system like you're talking about. They can't even afford these new constellation-style satellites, which are going to be $125 a month. But $30 for a little Texan shortwave radio sitting on the counter in the house gives them warning of cyclones. It gives them information about news of the outside world. And in a lot of cases, some of these islands, like Fiji, the news is being restricted by the government at various times, and it's often the only outside source of information that they had, and it's gone.
They also get to learn how to speak Chinese now.
Well, that's another issue. Is this working? I'm not sure.
That Talos group that you just mentioned is the group that is pushing the French government to get allocation in the 2 metre band for those low-powered satellites.
I was talking about the American constellation satellites. Yeah, but similar system.
Well, Talos is basically, I did some research on it, their home base is America, but they're using the Chinese because the Chinese have got an ear into this conference that's looking at...
I wasn't talking about GPS satellites, I was talking about down stations for internet. Yeah. Which are in beta at the moment at $120 a month, and the stations cost about $2,500 for the Earth station. Yeah. It's a lot cheaper, but it's still not affordable for those groups. Yeah. But now I forgot what I was going to say. I got sidetracked. Never mind.
We had a demonstration one night out at Tony's place where ISS was going over, and Graham had a handheld. I think it was a Bofung $35 one, and he was able to trigger the repeater on ISS with an ultra cheap radio. So we're making inroads into things that we do that we don't think of them in terms of the poorer nations of the world, but they would find that a much more achievable thing as an amateur in some of these poorer countries than what we would.
Well, amateur radio in a lot of poorer countries is actually a substitute for commercial services. Like in the Philippines, for example, the amateur radio clubs are service clubs, and they provide emergency communication services for various emergency responders like fire and police and that sort of stuff. And that's their regular duty, and if the people are a member of a club, they're expected to do that. Yeah.
I often wonder when I see how cheap these Bofungs are, just in those places like that, whether they don't in fact get programmed for the police, the fire brigade and the amateur bands all in the...
Oh, they do. A friend of mine in Azamas, he's a police officer, but he also happens to be an amateur radio operator, a Class B. They have 4 classes over there because it was based on the American system. He has a radio which is programmed for the barangay, which is the local government area frequencies, and it's programmed for the police frequencies, and it's programmed with some simplex amateur frequencies because they don't have a repeater there. All in the one radio. Nobody thinks twice about it.
Because one of the things that I didn't mention in the talk, but it's obvious, is that if you've got a decent transmitter and receiver pair that you're using, you've got the infrastructure there that will accept encryption into it down the track, as seen what happened with the police here in Victoria, where they went from analog wireless listening to now virtually 90% of their communications is on digital, and you can't unencrypt it. So, it leaves itself open to that sort of modulation into it.
I wasn't quite clear on some of the aspects of the multiplexing system that you showed us with single sideband there, Mike, but I understand that could be used for a multi-channel link from point to point, say across the Pacific, for example. Were you proposing that a system like that could be used for amateur services?
I don't see any reason why not. I mean, we don't use a fraction of the channels that are available to us in the HF spectrum. The fact that we ignore the opposite sideband above and below 10 megs and we don't use it. One of these nights somebody's going to come up using the other sideband to what you're using and frighten the living daylights out of it, because they shouldn't be doing that. There's no reason why they can't. It's done every day in commercial practice.
Right. Yep.
And I often wonder whether, and this is something that Graham just mentioned, there was a difference between a point-to-point, like say Honiara to Sydney. There's a path that's used every day, as opposed to Sydney to a cruise ship, and the cruise ship's moving around, and whether that would change the frequencies that you would allocate to the service, and whether there would be fades and so forth. The ships don't move overly fast, but I imagine as they move from area to area, there will be. But no doubt, they still continue to use that for radio telephone services to ships at sea, so it does work.
Yep. I'll just add something. Just thinking about the efficient use of some of the digital modes, not necessarily voice, but we use a mode like, for example, JS8 call on one frequency, so on 7078 on 40 metres, just one frequency that can be multiple conversations happening with, these are keyboard conversations, and it's actually quite amazing now how we've advanced with being able to use some of our digital modes on HF with amateur radio, and it reminds me of what some of the things that Mike was talking about, what they even did years ago with voice and so forth on HF. But so we're getting to the point now with amateur radio that we're really utilising the bands more efficiently for some of the digital modes, at least anyway. And with JS8 call, there's you can do a lot of networking with JS8 call, leaving messages on other computers and things like that. But it really is quite amazing when you can think we can use one frequency and have multiple digital conversations happening at the one time.
Those frequencies that I spoke about near the max, 700, 900, 1100, being 200 hertz apart, you can get some pretty decent sort of throughput of data rates with the 200 hertz bandwidth to play with. You'd know yourself from your JS8, if you open the bandwidth up, you can get it to work really, really fast. So.
Yeah, and the other efficient thing too with some of these digital modes is they're weak signal modes. So you can have a very noisy signal or not necessarily a lot of power, and they can work really well even in noisy conditions. So we've advanced quite a lot with how we utilise some of these digital modes.
It's interesting when you do the mathematics on, say, a 1 kilowatt transmitter, and you've got 9 channels there, what power per channel is actually available. And it's like you or I are doing a QRP audio on a net on HF. You maybe 5 or 10 watts to actually use, because the rest of it's shared out over the other channels that are available within the carrier.
I honestly believe that a lot of amateurs are missing an option, something that would help here. On HF and VHF, it's very common to use digital codecs to compress voice. In fact, DMR, D-Star, Fusion and several others do exactly that. And yet, every time it seems somebody suggests using digital codecs to compress voice on HF frequencies, the screams come out like murder and everybody gets up in arms about it. I mean, surely if we want to use efficient use, we should be putting voice into a 1 kilohertz bandwidth on HF frequencies using digital codecs. I mean,
we're going down that path, except for the last sentence that you put in there. We're narrowing and narrowing the bandwidth of voice to the point where it's almost getting unrecognisable.
Well, but that's because they're still analogue voice transmissions.
Analog. So the next step now is to say, okay, if we can get analogue through a 1.25 kilohertz wide bandwidth, how much better can we get digital through there? If we digitise the speech and feed into that bandwidth, how clear does it sound at the other end? An interesting experiment would be to set up a system like that, where you had, say, lower sideband and you're operating AM on it, and upper sideband and you're operating digital on it, and then compare the recovered sound, the quality of sound at the other end. It'd be interesting to do.
Yeah, I think so too. It was suggested in the United States, and the FAA didn't like the idea.
Yeah. No.
Sorry, well, not FAA, FCC.
Yeah.
Sorry.
FCC.
Too long flying.
And they've also made, I mean, I'm not an expert on it, but 3DV, HF digital mode, they've come a long way with the codecs for that.
Get around the restriction on voice modes. Oh, sorry. Most, I don't want to hog things. The thing is that there are a lot of amateur regulations around the world which restrict voice mode to certain particular types of voice mode under the regulations, whereas digital is not restricted in that way. So they can send JS8 or JT45 or whatever they want to send over digital, that's fine. But as soon as it's a voice codec, you run afoul of the fact that the regulation prescribes the modes that the voice can be. Whether, I mean, they used to have all those letter codes that I don't remember all these days, you know, but the 3-digit codes that they used to have to describe a voice mode and all that sort of stuff, and they're written into the regulations. So that's something that perhaps needs to be looked at down the track when they're talking about reviewing the regulations.
There's a book, I keep it at home because it's a wealth of information. It's the ITT Engineers Reference Handbook, and the copy that I've got's dated 1954. And it's got still the basics of all the means of stacking up frequency division, multiplex and everything else. It hasn't changed, but I'm wondering whether as the older generation of techs and engineers that designed all of that are replaced and we get newer ones in with better equipment to work with, better algorithms to use, whether we won't see some changes in what has been the accepted standard for a long, long time.
Well, they're not even teaching, they're not even teaching digital radio design in the same way that you showed the block module for the transmitters. The equivalent for digital transmitters is not actually being taught in the syllabus. And it should be. Because, I mean, if you go and have a look at the 7300 in there, that's not designed in the same way as what you're talking about on those diagrams in there.
No.
Yeah. Sorry, enough. Sorry. Yeah.
But I'm getting off the track, but I'm a firm believer that if you crash a plane in the Pacific Island and you smash up your radio, if you're a decent amateur, you should be able to make an attempt to get that thing going so you can call for help. And if you've just been taught black box technology, I'm afraid when you take the covers off, someone's taking the black boxes out because there aren't any in there.
Okay, are there any further questions at this point? No? Oh, Mike, this has been a very interesting presentation. Thank you very much. I know you put a lot of work into it, so well done on that one. And it's now coming up on 10 to 9, and so we'll break for supper. And to those of us online, thank you very much for your attendance this evening, and good night from the Bendigo Amateur Radio and Electronics Club, 73s.